Hello, this is Mr. Gilmore with the 9.7, the Special Segment Theorems. Today we're going to see some more interaction between our secants and tangents today, but our focus is not just on their angles like we saw in 9.6, but now we're going to be focused on their segments. So we want to broaden our vision now because we've considered a lot of arc and angle measures, but now we're actually going to be investigating segment measures with what we can do with our secant and tangent intersections. And we're going to cover a couple things before we dive into these. There are three possibilities, but we're going to find that through each of these three possibilities, these three theorems, that they're going to have common reasons or common justifications behind them. So I want to review with you a little bit of the reasons you're going to be using, and then we'll dive into those three possibilities. So we start with one of our first justifications we're going to be using today, which is actually a corollary of the inscribed angle theorem. Now recall with the inscribed angle theorem, it says that the measure of an inscribed angle is half the measure of the arc it cuts. Now, what we found then, as soon as we proved that, is that what if two inscribed angles are cutting the same arc? That means those two inscribed angles then are provably equal to each other. That was actually one of the very first inscribed angle theorem corollaries that followed from the inscribed angle theorem. And so in our diagram below, we actually have angle B and angle D. Notice that both of them are cutting the same arc AC, which means we can claim that those two angles are equal in measure. But at the same time, we also have angle C and angle A also cutting the same arc BD, which means, well, from the same corollary, we can claim angle A and angle C are equal to each other. Now, notice what happens then if we actually do label that point of intersection of those two chords, and let's call that point E. You notice that you've now got two triangles with two angles one equal to two angles another. That's going to lead us into our next reason that I want to remind you of, the angle-angle similarity. In angle-angle similarity, something we proved way back in chapter 7, we proved that when two triangles are with two angles of one triangle are equal to two angles of another, we've got similar triangles. Now, what we draw from that, the information we're going to actually pull from that, because our interest now lies with the segments, is that now we know that the corresponding sides of these two triangles are proportional, and that's going to lead us into our conditionals today, and actually what we're going to conclude about certain types of intersections that go on with our circles. So our first intersection we're going to find is our chord-chord intersection. So in our diagram, we actually have two chords intersecting on the interior of a circle. Essentially, it's where two secants intersect on the interior of a circle. And here's what happens. Remember, our interests lie not with the angles that are formed, but rather with the segments that are formed. Each of those two chords in the diagram actually cut each other up. Notice that where point E is, it cuts our first chord AB up into two smaller segments, AE and BE. And the second chord, CD, cuts our larger chord into two parts, CE and ED. Now, what happens then is what we're going to find is if we take each part or each piece of those two chords and we find the product of those pieces, that the product of those pieces will actually be equal to each other. So we take the pieces of our first chord, AE and BE, and we multiply them together. And then we take the pieces of our second chord, CE and DE, multiply those together. Those products are going to be equal. Now, I'm going to leave this proof up for you guys to do on your own, but I'm going to give you guys a push in the right direction. See, where you start in this proof is actually with some simple constructions. You begin by constructing a segment from C to A and a segment from B to D. Now, what you're going to find there are the two reasons that we just discussed on the previous slide. We saw the inscribed angle theorem corollary that talks about two angles that cut this, or two inscribed angles cut the same arc. That means they must be equal to each other. And the angle-angle similarity. From angle-angle similarity, you can then set up your proportions from your similar triangles, and you're going to find that with those proportions, when you cross multiply, you will end up with our conclusion that AE times BE will equal CE times DE. So where are your equal angles? We'll take a look at angle A and angle D. Those angles are equal in measure. Take a look at your angle C and your angle B. Those angles are equal in measure, which means there you have your two angles of one triangle equal two angles of the other, and then you can claim similarity between those. So there's all the puzzle pieces. You put those pieces together to form the proof of the chord-chord intersection. Let's take a look at our second intersection, the secant-secant intersection. This is where we find the two secants actually intersecting on the outside of our circle. So we have the segment AC and AE, those two secants. Now, there's another relation that we're going to find with relation of the segments that are formed here. Now, how this one breaks down is this. We're referring to the whole segment AC and AE as the secants. Now, you'll notice that because the secants intersect our circle at 2 points at point B and at point D, that there are these subsegments that are cut from the entire secants. Notice the two segments that are formed on the outside of our circle, AB and AD. That is where our relation is going to lie. That if you took the smaller segment there, AB, and multiplied it to the entire secant that we formed there, AC, and you took the smaller segment AD, this segment on the outside, and multiplied by the entire secant that's formed there, AE, then both of those products that we find there are going to be equal to each other, such that AC times AB is equal to AE times AD. And you're going to prove this one. Now, I'm actually going to help you with this proof. With this one, I'll show you the proof of the secant-secant intersection, and you'll see I'm going to use those exact same reasons as before, where I'm going to do some simple constructions. I'm going to find inscribed angles that cut the same arc, and I'm going to find a pair of similar triangles that I'm going to use to then set up my proportion. So let's take a look at this proof. So where we begin is with our secants AC and AE intersecting at our circle at points B and D. Let's then begin with our simple constructions of connecting a couple points together. So first, let's connect B to E, and let's connect C to D. What we find there are two overlapping triangles, ABE and ADC. We're going to prove those triangles are in fact similar to each other. We first begin by noticing that angle C and angle E cut the same arc BD, which means by the inscribed angle theorem corollary that the angle C and angle E are equal to each other. At the same time, because our triangles are overlapping, we can also claim that we have a pair of equal angles there. Angle A is equal to itself by reflexivity, which then means by angle-angle similarity, our two triangles ABE and ADC are similar to each other. So now on to the proportion we are going to grab. We're going to grab that we know that AE, the entire segment there, is then corresponding to the entire segment of AC, and that equals then AB, which corresponds to the segment AD, those two segments that are on the outside of our circle. And then we have a theorem that actually explains why we're allowed to cross multiply. We actually proved cross multiplication. It's the 7.1a theorem. So then we then cross multiply that proportion, and we end up with AE times AD equals AC times AB, which is exactly what we wish to prove. So there we have it, QED, the proof of our second possibility of the secant-secant intersection. We have one more possibility with the secant-tangent intersection. So what happens then if a secant and a tangent intersect at a point on the outside of our circle? Something similar to the last example happens. We actually end up then with a secant being chopped up into two subsegments, a segment on the outside and a segment on the inside. As it turns out, if we took the entire secant and multiplied it by that smaller segment on the outside, so AD times AC, it would actually equal the square of the tangent line AB. So we're going to prove that AB squared is equal to AD times AC. Now, I'm going to give you the puzzle pieces, and you're going to put this together as a proof on your own. So where we begin in this proof is, again, with some simple constructions. We are going to connect, actually, point B to C and point B to D. By doing that, we now actually have two similar triangles that are in fact overlapping, but in another special way, that the smaller triangle is actually part of the whole triangle. So we have this interesting part-whole similarity that's going on with our secant and tangent intersections. So now your goal is to find where those equal angles are. So the first angle pair that we're going to look at is obviously angle A is going to be shared between the two triangles. And the next angle pair is actually a little subtle to find, but here I'll point that out to you. It's going to be angle D and this angle here, ABC. Notice that both of those angles cut the same arc. They cut that arc BC. So why is it then that angle D and angle B are going to be equal to each other? Well, it's because angle D, by the inscribed angle theorem, cuts that arc BC. And angle B, ABC there, is not necessarily inscribed angle, but we do have a reason of why we know that angle there that's going to be equal half the measure of the arc it cuts as well. This angle ABC, we can justify that we know it's half the measure of arc BC from actually our previous lesson. It was case number 3 of the secant-tangent angle theorems. So that right there is our justification of why we know that angle ABC is actually going to be equal to half the measure of arc BC, which angle D is also equal to half the measure of arc BC. Thus, we know that those two angles must be equal in measure. So just keep that in mind, that's where we're going to find our equal pairs of angles from those justifications in this last example. So you now are good to go for angle-angle similarity, which means make sure you set up your similarity statement appropriately. Grab your pair of proportional sides that you're going to be involving, especially because you want to involve the segment AB, and you'll see it pair twice because it's going to be AB times AB when you cross multiply, and you'll end up with that AB squared. So there you have it. Those are all the puzzle pieces you're going to need to put that theorem together. You'll also find on this worksheet not only the room for you to recreate these theorems, but also you're going to see some application using these theorems in the next section. If you do have any questions on the 9.7 assignment, please do not hesitate to email me. I will get back to you. With that, be good and do good.